Hey, good morning. This is Mark Elsner. We'll allow another minute for people to join, and then we'll get started. Would somebody who's on the meeting, would you be able to send me a chat to confirm you can hear me? Thank you, Ms. Roman, Rhonda, Sean. Appreciate that. All right, I have 9:32 on 2 different clocks, so let's go ahead and get started. Hi, this is Mark Elsner. I'm the Water Supply Bureau Chief here at the South Florida Water Management District, and I want to welcome you to the Lower West Coast Surficial and Intermediate Aquifer System Groundwater Modeling Stakeholder Meeting. It was different today, and one of the advantages of a virtual meeting is we didn't have to get up at dark 30 to drive 3 hours over there. And one thing we found is with the virtual meetings too, it allows greater participation. So appreciate everybody joining in. This is a big day for the Lower West Coast water supply wise, and that we're conducting 2 meetings today. The first one is the Lower West Coast Surficial Intermediate model, and then this afternoon is the West Coast Floridan model. And this is a big milestone, and now we have 2 robust regional simulation tools that include all the aquifers used in the Lower West Coast. It updates models that were developed over a decade ago or something that's brand new. So it is important. It's going to provide us really good tools and looking at future water supply scenarios and guide us in our future decisions. But I do want to caution that modeling is not the end all. It just provides us another piece of information that helps us make decisions regarding water supply, and that we should consider these model results along with permitting information, monitoring information, wetland assessments, and other information that's out there. We always have to remain vigilant about our water resources. But for today's meeting, please don't take the results as absolute, but identifying areas that we need to pay attention to or need to be taken into account as future facilities are being designed and permitted. This is a technical meeting, so the presentations will contain more detailed information than an overview presentation. And we do have, warn you, with the complex aquifer system that we have over there, the presentations are somewhat lengthy because we have to talk about each aquifer system and the specific analysis that we've done for each of those. So we'll talk about that. We'll show the results of that. So for each item, we're going to go through the entire presentation, and then we'll take questions, comments, and have any discussion. And I'd like this to be a conversation. So if there's a question or a comment or just want to talk about it, please bring it up. I want to encourage you that if you think of something following the meeting, please get it to us. This is a Zoom meeting, so a couple logistical things is it has what we call a raise hand feature. So if you have, when we open it up for questions and comments, there's a raise feature on the screen. You have to raise your hand, and then Devon, who is our IT support on this, will go ahead and unmute you, and you'll be able to talk. If you're on a phone, you have to hit *9 to raise your hand, and then *6 to mute and unmute yourself. We will post these presentations on the website following this meeting. And we wanted to get these results to you ASAP. So we're currently finalizing the model documentation, and that should be available in the next couple months. All right, so let's get started. All right, our agenda today, like I said, there's 2 meetings. This was sent out Monday, but for this morning's meeting, I'll make some additional opening introductions. Then John Shaw, Principal Hydrogeologist here at the Water Management District, will talk about the recent update to the saltwater intrusion mapping. And then Uditha Bandera will, a section leader here at the district of the groundwater modeling section, will be presenting the superficial and intermediate aquifer model. And then we'll talk about the next steps. And like I said, there's another meeting this afternoon. It starts at 1:30, and that's on the West Coast Florida Aquifer model. All right, so our Lower West Coast Water Supply Plan, the last update was done in 2017. And as part of that effort, we did talk about these models under development, and that we would present those results when the models were completed and the simulations were conducted. So as part of that plan, the modeling is a big part of that, and we recognize that by with the recommendation of we need to complete the Lower West Coast superficial and intermediate model, as well as the West Coast Florida model updates, and then conduct the simulations. And as part of the water supply picture here, diversification is a really important part of this region. So I've said at several meetings, is the Lower West Coast is sort of an all-star in the way of diversification of your resources, water conservation, and development of alternative water supplies. For that Lower West Coast plan that was completed in 2017, our planning horizon was 2014 to 2040. We were projecting an increase of about 58% in population, from about 1 million to over 1.6 million residents. Public demand to support that growth, public water supply demand was going up 55% from 129 million gallons a day to 200 million. And overall, agricultural acreage is projected to stay relatively the same. So with all the demand sectors, we're projecting the gross water demand to increase from about 971 million gallons a day to about 1.2 billion gallons a day, or 25% increase. On the right shows public water supply withdrawals and sort of the diversification. So the 2 blue we're talking about this morning, that's the intermediate and superficial. And then this afternoon, we're talking about the gray bars. And part of the conclusions of the plan and working with the utilities is that we're going to continue to see the Florida aquifer withdrawals grow, and not much in the way of the intermediate and superficial. And you can see that that's remained relatively stable over the last several years. So why is this important? Over 70% of the water used in the Lower West Coast is derived from groundwater. On the right, you will show dots for all the water use permits that use an aquifer system for their supply. And with the color dots, you can tell where the aquifer is present and where it's not. Lower Tamiami is the blue and is primarily present in this area, whereas you go north, it transitions into the Sandstone and Water Table and mid Hawthorne. This fish walker system is a major water supply source, and as part of this effort in our water supply planning is sustainability of the water resources. So as we grow, we need to make sure that those water resources are going to be available for generations to come. All right, so with that, I'm going to go ahead and turn it over to John Shaw, and he's going to be talking about the 5-year update to the saltwater intrusion mapping here at the district. Okay, John.
Yep. Okay, thank you, Mark. This is John Shaw in the Water Supply Bureau at South Florida Water Management District. And this morning I'm going to be giving about a 20-minute presentation on the 5-year saltwater intrusion mapping update. We're going to, let's see. We're going to start with an overview of the saltwater intrusion mapping process, which is it's a district-wide effort, and then we'll focus in on the lower West Coast. This information is not directly input into the models that we'll be discussing a bit later, but it does serve many uses, including being used as a tool to understand some of the changes occurring in the aquifer. We're also going to talk about the importance of, let me get this out of the way, importance of well fields and infrastructure, our project approach, and then again, looking at the results for the lower West Coast. We'll have some conclusions, recommend some next steps, and then some questions and discussion. So there are several sources of saltwater intrusion, and probably the one that you're most familiar with is lateral intrusion from the coast. The saltwater being more dense, underlying the fresher water in the aquifer. But you also have vertical intrusion, which can be from upconing from saltwater that underlies the aquifer. You could have it from the surface infiltration from estuaries, boat basins, saltwater marshes, saltwater canals. Again, we found in places in, for example, Broward County, where they have a lot of saltwater canals connected to the ocean, that there is a lot of infiltration into the superficial aquifer. And then something that we occasionally see is what we call ancient or relic seawater, which has been trapped from geologic time into low permeability aquifers. And this actually does come into play in the lower West Coast, and we will discuss that as well. The district's program addresses the coastal counties within our district, with the exception of Miami-Dade County, which is the saltwater intrusion mapping is done by the U.S. Geological Survey. So we cover St. Lucie, Martin, Palm Beach, Broward, and Lee and Collier counties. And you can see the lower West Coast planning region overlaying on the Lee and Collier counties, and certainly includes the coastal areas. And we will be discussing those 2 counties within the lower West Coast region. Looking at the generalized hydrogeology, on the East Coast, we have the Biscayne, primarily the Biscayne aquifer in the water table. But for the West Coast, there's an email over my pointer. There we go. So over in the West Coast, you can see the water table aquifer, the lower Tamiami aquifer, the Sandstone aquifer, and the mid Hawthorne aquifer. So as you will see, there are separate plots of saltwater intrusion in those 4 aquifers. And why is this important? Well, we are trying to protect the well fields, which are obviously a major source of water supply. They're an investment that need to be protected. And once the saltwater enters into the aquifers that are penetrated by these drinking water wells, it's very difficult, if not impossible, to reverse. It's very expensive to relocate the well fields and the associated infrastructure, pipelines, treatment plants, and so on. And then if you have to go to other sources, deeper sources typically, such as the Floridan aquifer, you would then have to use reverse osmosis treatment, which also creates a brine reject, and you'd have to install deep injection wells, which is also a very costly effort. So looking at the district's mapping project for the saltwater interface, our strategy is to compare the position over time and note the areas of concern and adjust monitoring as necessary. So this has been happening every 5 years. You can see we have maps for 2009, 2014, and now we'll be talking about the 2019 maps. We use all the available data that we can get our hands on from the USGS, from the district, counties, and a big portion from our water use permittees. We're also looking at a worst case scenario because we're looking at the furthest inlet extent at the end of the dry season. So this would be the maximum chloride value for March, April, or May, in this case 2019, with some very minor exceptions. We mapped the 250 milligram per liter chloride line, which is also the drinking water standard. And just a quick warning, if you are looking at the USGS data in Miami-Dade County, they mapped the 1,000 milligram per liter line. And again, we look at all of the upper aquifers, the water table in the West Coast, known as the Biscayne on the East Coast, the lower Tamiami, the Sandstone, and the mid-Hawthorne aquifers. There are challenges to preparing these maps. One of them is that we're representing a 3-dimensional feature, that being the saltwater interface, freshwater saltwater interface, on a 2D map. We're representing a dynamic interface with a single point in time. And again, ours being the end of the dry season. Mapping, it could be from several different pathways. I talked about that earlier. And again, as you'll see in Collier County, we have some connate relic seawater. So it could be coming in from different ways. It could be coming in from the surface. And just some of the practical aspects. Some of the wells that we may have used in 2009 and 2014, they may not be available. In 2019, they could have been abandoned, destroyed, or no longer monitored. Or there could be new wells, and we'll see some examples of that, where new wells have altered the interpretation of the isochlor line. And also the existing well construction spacing, the depth, and again, things like screen interval, and we'll see how that affects the line as we move along. There are other considerations, as I said, such as the well construction. Where is the screen? Is it a long screen, a short screen? Is it at the top of the aquifer? Is it at the base of the aquifer? Sampling techniques can vary. Even the parameters. Sometimes it's chloride, sometimes it's conductivity. The frequency can change. Sometimes it's quarterly, sometimes it's semi-annually. And one of the issues that we found out, if you noticed, I said, except with some exceptions, we were looking at March, April, May. Well, some of the permittees, they may sample semi-annually. So if they sample in January and June, we don't see that data when we look at it at the end of the dry season. And this came into play in a very important well field area in Broward County. So we looked at the data a little closer, and occasionally we'll widen that time period to include some additional data. And again, your analytical methodology, are you using test strips, are you using hack kits, are you sending it to a laboratory? So all these things affect the chloride values or the way the isochlor line is plotted. So this shows, again, as I have mentioned, this is a district-wide effort. So we generate a number of different maps, but I've shown here in yellow the ones that we're going to be focusing on today for the lower West Coast. Lee County has a water table map. It has, and then for the Sandstone, we do Lee and Collier. We also do Lee and Collier for the lower Tamiami. We do a water table map for Collier, and then the mid-Hawthorne is shown in both Lee and Collier counties. Okay, so now we're going to start talking about the plots, and unfortunately, this is one of the disadvantages of having a Zoom meeting, because typically these maps are plotted on a plotter, so they're typically 36 inches wide, and they can be as much as 60 inches long. So they're very big sheets, and we normally put them up in the auditorium or wherever we're speaking, and people can look at them. Well, you're not going to be able to look at a whole one, and it's difficult to, take something that's, 3 feet by 5 feet and project it on a screen. So I'm going to break it up into its pieces, and we'll talk about the pieces, and then you can imagine them all being together on one big map. So the legend includes things like structures, culverts, pumps, spillways. These are actually very significant, again, particularly on the East Coast, where we call these salinity barriers. And that's the point. These structures are made to keep the water level high and prevent the salt water from moving up the canals. The maps have dots. There's green means that your chloride concentration is less than 100 milligrams per liter. A yellow dot means it's 101 to 250. Orange is 251 to 1,000. And red means greater than 1,000 milligrams per liter chloride. Each sampling point has two numbers. The first number is just strictly a numerical map ID number, and then the number in parentheses next to it is the chloride concentration value in milligrams per liter. The maps also have 3 lines on them. The red line is your 2019 isochlor. The green dash is the 2014 250 milligram per liter isochlor, and then black dots represent the isochlor line from 2009. In the background, we try to show well fields, some freshwater bodies, saline water bodies, and then mangroves and saltwater marshes. Then along the bottom of these big plots, we have a listing, again, numerically. This is an example of one, and typically there's at least 3 columns of these. So this one goes from 1 to 32. We typically have over 100 wells on each one of these maps. So this is just one set of information that's shown at the bottom, where we just start with the map ID. A lot of these wells are in our district database, so they have a facility ID number, a project name, a well name, your XY coordinates, and then your case depth, your total depth, and then the last column gives you your chloride value. On the sides of the plots, we do some time series. And again, as I mentioned, the green, the yellow, and the orange, this one doesn't have any red, but we map it with time. And the idea is it works a little bit better on the East Coast than it does on the West Coast. But typically your wells to the west of the isochlor line are certainly going to be higher than 250. And if you note, both of these have the 250 milligram per liter line demarked. And so the eastern side, which it would be your fresher side, would typically have lower chlorides, and hopefully the trend, like here, you can see it started to go up a little bit, but with time it came back down, and that can also be a function of how dry the dry season is. But in any case, so there's a number of these that you'll see when you look at the maps displayed around the sides. So here we go with the first actual isochlor map. Again, I added the legend just to so you can tell the isochlor lines. The red being 2019, the green being 2014, and the black dots, which kind of overlies the green here, is the 2009. For the water table aquifer in Lee County, there were relatively few changes, and as I'm showing here, there's actually some improvement, which is probably due to this new data point here. So as I mentioned, new data points may result in reinterpreting the line. So when this came in at, I think that's 95, we needed to put the line on the left side of it, and which shows some improvement. For the Collier County water table, I'm going to be zooming in on a couple of areas here. So this is just the whole county map, but let's take a look at a couple of areas of interest. Okay, so this is just a blow up where you see in the Naples area, it's fairly stable. However, we do have some areas here by the Lehigh and the Henderson canals where we're seeing some movement. And we believe this is due to some new development near the coast, where we've got some tidal areas where it ranges from fresh to saline. So what we do with these permittees is make sure that they're monitoring for chloride concentration in groundwater, and that information is reviewed by our regulation division. Looking at the Lee and Collier County Lower Tamiami, again, it's relatively stable near the Coastal Ridge well field, which is good news because that is a Lower Tamiami aquifer well field. We do show some retreat in the Bonita Springs and the Collier County area. And then this here is our example of the Relic Seawater. This is a well-known feature that has been documented by the U.S. Geological Survey of basically, again, trapped seawater, and we can see that interface. The Sandstone aquifer, we got some new monitor wells, and so the chloride concentrations have fluctuated, and I think we're talking about these points here where the line moved with the addition of these two data points. And looking at the data from a time series perspective, they do seem to, the chloride concentrations go up towards the end of the dry season. There is some landward movement also in the Buckingham and the Lehigh Acres area near FGCU, which also has a couple of new monitor wells that have been added to the monitoring program. The mid-Hawthorne, again, we got a new data point, and so we are, that permittee is monitoring those chlorides, and we do see that they tend to be high towards the end of the dry season. So in conclusion, the water table aquifer, we've seen some noticeable landward movement around Lehigh Canal and Henderson Creek. For the lower Tamiami, the interface has retreated in northern Lee and southern Collier counties, and it has advanced in some areas also in Collier County, where it's gone both ways, both retreated and advanced. The interface is dynamic, and it can depend on well field pumpage, reclaimed water use, tides, sea level rise, and other factors. Saltwater intrusion is occurring, which emphasizes the importance of continued monitoring, both laterally and vertically, as well as well field management. And we know a lot of the well field managers, they do adjust their wells depending on rainfall. And additional localized monitoring may be required at specific projects by the permittees to protect the water supply. So some of our next steps are continue to work with local governments, and I do appreciate the help of the lower West Coast governments that have been collecting some of this chloride information, and as well as other permittees to identify the other existing wells to increase the mapping accuracy in the future. Consider sampling frequency. As I mentioned, if you're sampling in January and June, it may be missed in this particular program. Identify funding to facilitate well replacement as needed, and then look at some of these areas of concern or gaps where we may need to put in additional wells. So those of you that want to actually look at the or download or plot these maps, they are available on the district webpage at this location here. You can get all three of the years, 2009, 2014, and 2019. And for those of you that are GIS inclined, we also have merged isochlor data for 2019, and the same with the chloride. And we actually may have that for all 3 years at these district web pages that anyone can access. Or if you have questions, you can email me or call me at this number. I'll be happy to help you. And with that, Mark, I'm not sure if you want to take questions now or later, but I'm available.
Yes, we'll take them now. Just a reminder that we will have the presentations posted on the website within the next day. And that'll be on the Lower West Coast website. And I think Bob will send out a reminder that they're available. All right, if you have a question or comment for John, can you raise your hand with the raise hand feature as part of Zoom? Or if you're on a phone, *9. All right, I'm not seeing anybody raise their hand. Oh, there we go. I see Eric has his hand raised. Looks like you can talk now, Eric. Thanks.
Yeah, during your presentation, you mentioned one of the challenges was the interface is not, horizontally well defined. You got the top and the bottom of the interface. So when you map the isochlor, how did you decide where to map it? Was it the top, the bottom, the middle, or some other?
Well, yeah, it depends where the well is open to. So, we're really dealing with, we try to get essentially fully penetrating well to the base of the aquifer. That's our preference. But, we have to deal with the data that we have.
Thank you.
All right, Kirk, I see you have your hand raised.
Yeah, Mark, thank you. First of all, great graphics. This is some of the best graphics I've seen you guys produce lately, so very nice. I just want to make a comment on that inland movement up the Tamiami isochlor in Collier County. I'm familiar with that site. I agree with John. I think there's some associated construction dewatering that led to that. But if you look at the time series for those data, the biggest change occurred the day of Hurricane Irma. It's really a cool graphic if you want to take a look at it. I think there was a major tidal inundation from Hurricane Irma that really pushed that whole thing in right there in a single day.
Yes, thank you, Kirk, and hello. We see a lot of that on the East Coast too, where you just get big big tidal influx and storm surge.
It's a good comment, though. All right, any other comments or questions for John? All right, John, thank you.
All right, thank you.
All right, let's move on. We have Juditha Bandera, the section leader for the groundwater modeling section, who will be talking to us about the model and the results. All right, Juditha.
Yep, thank you, Mark. Good morning, everyone. This is Juditha Bandera with the Groundwater Modeling Unit. So today I'll be talking about the calibration and application of the low viscous superficial and intermediate aquifer system model. Right, let me see if I can.
Sorry, I moved the cursor there. Okay, you got it.
Okay. Here's my agenda. And first, model objectives and overview, and then I'll talk about the model calibration, and then I'll move on to the model application. Basically, we have simulated two scenarios, 2014 reference condition and 2040 future condition. And then I'll share with you some of the head difference maps that we produced. And then I'll talk about the wetland impact analysis that we did. And then I'll talk about the maximum developable limit or the MDL analysis. And then the velocity vector analysis. And then finally, I'll talk about the conclusions. The model objectives. The main objective of this model is to support the low viscous planning or supply planning process. So we will be using this tool to basically evaluate if the current and future conditions are sustainable. More specifically, we will try to identify the areas of wetland that can be potentially get impacted due to the increased cumulative withdrawals. And also, we will try to identify any potential saltwater intrusion issues in coastal aquifers. Model overview. What you're seeing here in the figure is the location of the model. So the model boundary is shown in the red box. This is the model boundary. You can see my cursor. And then there's another boundary shown in yellow. This is the low viscous planning area boundary. So we pretty much cover the low viscous planning area. And so this model includes entire Lee County, Collier County, Henry County, and portions of Charlotte, Glades, and Monroe counties. About the boundaries, on the west, we have our boundary coincide with the Gulf of Mexico. And then on the northwest portion, we have aligned with the Peace River. We have aligned our eastern boundary along the district's primary canal network that runs from north to south. And from northeast corner, we have aligned with the Lake Okeechobee boundary. And from south, we have aligned our southern boundary along the Los Mans River and Big Los Mans Bay tidal boundary. And northern boundary, we have a specified head boundary because we could not find any physical feature to establish this boundary, but that's a reasonable distance away from the areas of interest. Continuing model overview. And I just want to mention that this is the first district model that simulates both superficial and intermediate aquifer system that covers the entire planning, low viscous planning area. And so we sort of developed this model from scratch. It's a big effort. And we've spent a few years developing this model. And a lot of good data went into the development of this model. Among them, updated hydrostratigraphy is one of the key information that we use for our model layering. And we do have a publication available to public if you want to look at this report. This is a mud flow based model, and we have a uniform grid size of 1,000 feet by 1,000 feet. And we use monthly stress period, meaning our time varying data input interval is 1 month. And the other important thing I want to mention here is we incorporate reclaimed water through golf course and landscape irrigation return flows. Historically, we haven't incorporated reclaimed water, but more recently, we've started incorporating this process into our groundwater models. So we've calibrated this model for the period starting from 1999 through 2012, and then we verified our model for 2013 and 2014. And then we did calibrate our model for surface water flows, surface water stages, and also groundwater levels. And the other point I want to highlight is that this model went through an independent scientific peer review. We just completed the process. It actually happened concurrently with the model development. So in the panel, there were 3 experts in South Florida hydrogeology and groundwater modeling. So they provided us very good comments, especially regarding to evapotranspiration, recharge, and the water budget analysis, and also regarding the calibration criteria. So we incorporated all the comments from them. All right, about model layering. What you're looking here is, you've already seen this figure, cross-section of the generalized hydrogeology of low west coast area. So basically we have in low west coast area 3 major aquifer systems. The first one is official aquifer system, which is the low water table aquifer and the lower Tamiami aquifer. And then we have the intermediate aquifer system, which is the Sandstone aquifer and mid-Hawthorne aquifer. And then the Floridan aquifer system. Today, I'll be talking just about the superficial and intermediate aquifer system. We do have just like Mark pointed out, we do have a model for the Floridan aquifer system also, which will be presented in the afternoon. The reason why we have 2 different models is, for the most part, there's no hydrologic connection between Floridan aquifer system and the superficial system. So we developed our layers, model layers based on the hydrogeologic information. So we have a 9-layer model starting with water table aquifer, then lower Tamiami aquifer, and sandstone aquifer. I want to point out that we split sandstone aquifer into 2 zones, clastic zone and carbonate zone. This was based upon the updated hydrostratigraphic report. And then finally, the last model layer is the mid-Hawthorne aquifer. And in between these productive aquifers, we have semi-confining units. So essentially, it's a 9-layer model with 5 productive aquifers. Right. With that, I want to move onto model calibration. So first, I would like to talk about the surface water calibration that we did. In Southwest Florida, there's a strong connection between the superficial aquifer system and surface water, especially with the superficial and intermediate aquifer system. This happens through mainly wetlands and rivers. So basically, we wanted to ensure that the surface water flows and stages are reasonable, because that clearly impact our groundwater recharge. So we have a surface water and unsaturated zone model, which are simple models that we coupled with the mud flow groundwater model through ET and recharge, evapotranspiration and recharge processes. And then we calibrated our surface water flows to the observed structure flows at 2 major watersheds, East Caloosahatchee watershed and West Caloosahatchee watershed. And we looked at several calibration statistics. Here's my calibration summary. Basically, the statistics represents how well the model captures the transient response compared to the observed data. And we establish our calibration criteria based upon previous models and also from recommendation from the peer review panel. And in the table, the green font indicates that we meet all the calibration criteria for both East Caloosahatchee and West Caloosahatchee watershed. And moving on to the surface water stages calibration. Now, in our groundwater model, we use wetland package to simulate overland flow over the wetlands, so we can directly compare simulated water levels with observed water levels in wetland areas. So we had about 60 wetland target stations that are shown in this figure that we use to compare with simulated water levels. And here's a summary of my calibration statistics. Basically, we've looked at various calibration statistics. And again, the calibration criteria was established based upon the previous models in the region and also from the recommendation from peer review panel. And again, I'm not going to go into the details, but green font indicates that we meet all the calibration criteria. Moving on to groundwater level calibration summary. We actually had 444 target groundwater monitoring wells, and the locations of the groundwater monitoring wells are shown in this figure. And the colors represents various aquifers that they belong to. Yellow or the brown color represents the water table aquifer, and purple color represents the lower Tamiami aquifer. As you can see, most of the monitor wells are located in water table aquifer and lower Tamiami aquifer. There's very little information on Sandstone and mid Hawthorne compared to the water table and lower Tamiami. Here's the summary of my calibration. So we looked at the same calibration statistics, and for each aquifer, we established calibration criteria, which is essentially the same calibration criteria. Again, this was based on previous models and the peer review recommendations. And as you can see, green font indicates we meet all the calibration criteria that we established for each of the aquifer. So once we meet all the established calibration criteria, then we have the confidence about the model. Then we can move on to the, basically doing the scenario simulations. With that, I want to move to model application. Right. Basically, we have two scenarios. One is the reference condition, which is 2014, against which we compare the future condition, which is 2040 run. So essentially, these two runs are similar to the calibration run in terms of the simulation period, which is 16 years, and also similar climatic conditions, meaning we have same rainfall and same evapotranspiration data for these two runs. The difference is the pumpage conditions. So the table here shows how we derived the 2014 and 2040 pumping conditions, the pumping data that we put in the model. So in 2014, public water supply values were used as reported, and agricultural recreational data was estimated using another numerical model called AVSIAS. This is the model we generally use to estimate irrigation demands. And then the domestic self-supplied demands were estimated using the per capita use at each county. And then 2040, all water use, including public water supply, agricultural, recreational, and domestic self-supplied, were projected values from the plan. And then the commercial and industrial values, actually, those are very small amounts within the low viscous superficial and intermediate aquifer system. So we basically used the permitted allocation for both 2014 and 2040 runs. Okay, one thing I want to point out here regarding the 2040 conditions. So the increased demands were assigned to the existing wells in the case of public water supply. And in the case of agricultural and recreational demands, we actually created some new wells within their planning boundary. And for the DSS wells, we actually used locations identified in the population projection for DSS. And then on the right-hand side, you can see a bar chart showing the simulated 2014 and 2040 groundwater pumping. As you can see, for PWS, there's only about 18 mgd projected to be increased. and there's no projected increase for agriculture. And there's about 15 MGD projected to be increased for recreational, and there's 13 MGD for domestic self-supplied, and no increase for commercial and industrial. And in total, you see about 45 MGD increase. That's just the groundwater from superficial and intermediate aquifer system. All right, I quickly want to point out one limitation in our demand simulations. So in 2040 simulation, the simulated demands are instant on, meaning that we do not have a annual growth in the simulated demands. So I'd like to explain that using the graph here, where we have plotted the demands against the simulation period. So the blue line here shows the 2014 demand, simulated demands, which is 606 MGD. And then for the future condition, 2040 condition, you would expect you would use something like gradual increase that I'm shown here with the dotted yellow line. We would use something like this, but because that's what generally happens. But in the simulation, what we have done is we have used the entire total demand starting from the simulation period. We start off our first stress period with that demand and continue throughout that for the entire simulation period. So essentially what this means is the simulation results that you are going to see are conservative. And some general regional model limitations that I want to talk about. First one is the heterogeneity. Being a regional model, we are using 1,000 feet by 1,000 feet cell size. So we may not be able to capture all the local variability in aquifer properties, and therefore we may not be able to capture responses at each individual well. And the other point I want to talk about is the, there are a lot of situations where we encounter, we have multiple wells in a single model cell. Now, what the model does in this kind of situation is model aggregates all the withdrawals at the center of the model cell. So what this does is this actually tends to exaggerate the port level drawdowns. So essentially what this means is the results are going to be conservative. So the takeaway message of this slide is to basically the model results that you are seeing from this kind of a regional model should only be used for planning purposes. Results should not be taken as absolutes. All right, what I'm showing here is the location of pumping wells, all the pumping wells that we used in the model within the Lower West Coast planning area. Now this includes public water supply, agriculture, BSS, and commercial and industrial. And on the left-hand side, you can see their locations, and the colors indicate that aquifers that they're pumping from. Water table aquifer is shown in brown color. You can see some dots. And lower Tamiami aquifer you can see in purple, in Collier County and Henry County. And also Sandstone aquifer in blue and green and blue. You can see some in Collier County and Lehigh County. And then mid Hawthorne, you can basically see in Cape Coral area and some in Marco Island. And looking at the volumes, if you look at the pie chart, you can see clearly the lower Tamiami aquifer is the most used aquifer. It produced 241 million gallons per day in 2014, which is actually about 40% of the actual groundwater use within the superficial and intermediate aquifer system. And the least used aquifer is the Mid-Hawthorne aquifer, which produced about 39 MGD, which is about 7% of the total groundwater use within the model domain. Okay, here I just want to quickly show you the locations of the largest public water supply permits in the superficial and intermediate aquifer system. On the left-hand side, I'm showing the locations. You can see Lehigh County Utilities and then Bonita Springs, City of Naples. We have 2 well fields, Collier County and then Marco Island. And then on the right-hand side, I'm showing the current allocations and then 2014 simulated demands and 2040 projected demands that we simulate in the model. And then also I'm showing the difference between the 2040 demand and 2014 demand. So essentially, we don't see a big increase in public water supply. The biggest increase that we see from the city of Naples, which is about 6 million gallons per day. And then, as I mentioned earlier, we see 2 well fields for city of Naples. This entire demand comes from this eastern well field of the city of Naples. And the other thing I wanted to point out is, you can see in this table, there are some situations where we have simulated the projected demands above the current allocation. And that's because this is just a planning tool. I mean, we are using this as a planning purpose. And so there's no guarantee that, you know, the Water Use Bureau will permit these numbers. This is just for planning purpose. And in this slide, I'm sorry, hold one slide ahead. Okay, so I'm showing here the largest agricultural permits in the model domain. So on the left-hand side, you can see the agricultural permits are mainly, biggest ones are concentrated around the tri-county intersection area, which is Lehigh County, Collier County, and Henry County. And also we can see some large users in Henry County and in Charlotte County. And the table again shows the permitted allocation and 2014 demand that we simulated in the model, and 2040 projected demand, and also the difference. And there's not a lot of increase throughout the model domain. And what we see is actually there are some decrease in projected demands in some of the cases. So the net result is actually there's no major increase in ag demands. Okay, then I would like to move on to the model results. So in the next several slides, what I'm going to be showing is the simulated heads, or you can call it water levels differences. Basically, I'll be looking at 2040 future average condition minus the 2014 reference condition average values. Okay, looking at the water table aquifer, I just want to talk about the color ramp first, the legend. So the beige to red color shows drawdown in this figure, and light green to dark green shows rebound. And the gray color indicates aquifer absences. So looking at the map, we can see the biggest drawdown is occurring somewhere in the tri-county intersection area, which is about 3 feet. Actually, this happens because of some of the pumping that is occurring in lower Tamiami aquifer and Sandstone aquifer underneath. And the other thing I want to point out here is if you look at the Cape Coral area, you can see some rebound occurring. It's about 1 foot rebound. And this is actually happening because of the some of the decreases in pumping in mid-Hawthorne aquifer. Now in this area, if you're familiar, we don't have lower Tamiami aquifer and Sandstone aquifer. They both pinch out. And we have water table aquifer, then we see the mid-Hawthorne aquifer. And the other one I want to point out is the rebound that you see in Eastern Henry County. This is actually because of some of the decreases in pumping in lower Tamiami aquifer. This happened because the district has purchased this area for restoration purposes, and so therefore there won't be any future demands in this area. Right, moving on to the lower Tamiami aquifer. So you can see the lower Tamiami aquifer pinches out when it goes to north, west, and north area. So the biggest drawdown you see again near the tri-county intersection area, Lehigh County, Collier County, and Henry County. And then this drawdown is about 3 feet. And this is because of the combination of agricultural, PWS, and some recreational wells. And again, you can see this rebound occurring here because of the decrease in lower Tamiami agricultural pumping. And moving on to Sandstone Aquifer clastic zone. So you can see the biggest drawdown is occurring in Lee County, again near the Tri-County intersection area. And this time the drawdown is about 12 feet. And again, this is due to a combination of public water supply, agriculture, and some recreational well increases. And moving on to the Sandstone Carbonate zone, and we can see the biggest drawdown occurring at the same area. Now this time it's about 15 feet. And one thing I want to mention here, there's a significant increase in projected domestic self-supplied wells in Lehigh acres in this area. So that attributes a lot to this drawdown that you're seeing here. And moving on to the Mid-Hawthorne Aquifer, you can see a biggest rebound occurring near Cape Coral area. This is due to the decline in DSS pumpages because of the public water supply service area increase and also the increased use in reclaimed water in this area. And you can see some drawdowns in Western Collier County, which is about 12 feet. And then some drawdown in Western Collier Lee County, which is again about 12 feet. And one thing I want to mention here is that Mid-Hawthorne Aquifer is not a very productive aquifer. So even for a small amount of pumping, you will see a big drawdown. That's why you see big drawdowns here and big rebounds also. All right, then I would like to move on to the wetland impact analysis. This one we achieved using the pump source scenarios. Okay, the purpose, basically, we want to identify any wetland areas that will be potentially impacted by the increased water use withdrawals. And we have a couple of limitations in this type of analysis. The first one is, now the model is calibrated with all the pumps turned on. But in this case, what we are going to do is we are going to turn off pumps. Then that will actually make the calibration less reliable. So the calibration statistics won't be as good as what you saw previously. And the other important thing is we know the drainage and other development features negatively impact on the wetland system, but we do not consider that in this analysis. All right, wetland impact analysis. So the method, this is a multi-step process. And essentially what we do is we use 2014 and 2040 future condition runs, and then we turn off pumps in both condition, and we run scenarios under pump off condition. And then we overlay the wetland 2014 wetland coverage. And then we try to identify wetland areas with a potential 1 foot or greater of additional drawdown in water table aquifer. So we are just focusing on the water table aquifer. Now in the figure, the right-hand side, you can see the green areas represents the wetlands. And the red areas are areas with 1 foot or greater of additional drawdown underlain by wetland. So you can see some in Collier County, some in Lee County and Charlotte, and some in Glades County, and also some in Henry County. And also you can see some improvements occurring in southeastern Henry County because of some of the decreases that we saw in the agricultural demand. So these areas are getting better. And then the maximum developable limit analysis. So the maximum developable limit, or the MDL, actually they're part of minimum flow level prevention strategy. So they are in place in order to prevent any harmful withdrawals to the lower Tamiami, Sandstone, and mid-Hawthorne aquifers. The MDL line is basically a hypothetical line which is drawn 20 feet above the aquifer top. And the rule says during 1 in 10 drought conditions, you cannot draw down the aquifer water level below this line. So I will use this figure to explain. I have the Sandstone aquifer example. So in the figure, you can see the bottom line in blue. This is the aquifer top. In other words, this is actually defined as the minimum flow level of the aquifer. And then the dotted blue line represents the maximum developable level, which is the MDL, which is drawn 20 feet above the top of the aquifer. And then usually the sandstone aquifer head is way above than this. So you can see in cyan, the cyan line represents the sandstone aquifer water level. So what the rule says, during 1 in 10 drought condition, you cannot draw down the sandstone water level below this dotted line, which is the maximum developable limit. And for our modeling purpose, we came up with the 1 in 10 drought condition, looking at all the historical rainfall data. Because our simulation period goes from 1999 through 2012, we have picked 2007 as the 1 in 10 drought condition. However, I want you to keep in mind that 2007 is a very dry year. It's actually a worse condition, much drier condition than 1 in 10 condition. But because within this period we had to pick an year, this was the closest one. So we picked because it represents a conservative case. And then I would like to talk about the 2014 Lower Tamiami Aquifer MDL analysis. And the procedure is very simple. So basically, we create 2 raster surfaces, one for the top of the aquifer and the other one for the simulated head during the 1 in 10 drought condition. Now, because the model works on monthly stress periods, so we picked the 2007 May condition as the worst condition. So we developed a raster for the simulated head in 2007 May. And then we removed the areas of the lower Tamiami aquifer where the aquifer is absent. And then essentially what we do is get the difference between these 2 rasters, which is the lower Tamiami simulated head minus the lower Tamiami top. If you see the difference is less than 20 feet, it indicates a potential violation of the MDL. Now, the figure here shows that difference, which is the lower Tamiami simulated head minus the lower Tamiami top. Now, in the black areas indicate where the aquifer is absent. And if you look at the color scale, what blue indicates is it's greater than 20 feet, which means we meet the MDL criteria in everywhere in the domain, except for this very little area. Also in the tri-count intersection area, we see the values somewhere between 5 to 15 feet. So that's an area where a potential MDL violation can occur. So I'm going to zoom into that area, this next slide. And in fact, when we closely look at this particular area, what we noted was, we noticed that there's no confinement above the lower Tamiami aquifer. So there's no hydraulic separation between the water table aquifer and the lower Tamiami aquifer in this area. So essentially it behaves as water table aquifer. So this gets, MDL analysis difficult because of, difficulty in defining the aquifer. And on the other hand, we looked at some, there were a couple of monitor wells in this area. We looked at the monitor wells. During 2007 May, we did not notice that these actual water levels violated the MDL criteria. That's, we believe, mainly because it was measuring the water table aquifer water levels, which is higher than the lower Tamiami aquifer levels. And in fact, in this case, you have a single aquifer. And the other point I want to make here, when we looked at this area, we noticed there were a couple of agricultural withdrawals associated with these high drawdowns. And then the way we simulated in the model, we use APSIS, which is another numerical model to simulate the, to estimate the agricultural demands. The reason for that is because we don't have the meter data available to use for the agricultural withdrawals. Now that's a big limitation in the model because when we do the APSIS estimation, we make several simplified assumptions. For example, we assume every inch of the permitted area is fully drawn, which may not be the case in the field. So that's one of the big limitations. And then we also looked at the Sandstone aquifer, and the model indicated that a small area in northern Collier County, near the border of the Henry County, MDL, there's a potential for MDL violation. And again, what we noted was, we noticed that there's no confining zone just above this area between the lower Tamiami aquifer and the Sandstone aquifer. So that makes the MDL analysis difficult because of the difficulty in defining the aquifer properly. Also, we noticed that there were some agricultural withdrawals associated with this potential vulnerable area. And then when we looked at the projected demands, what we noticed was there's no future growth in this area. Actually, we see some decline in the projected demands. So that makes, in the future, there's less likely that the MDL will be violated in this area. Okay, then moving on to the velocity vector analysis. So first, keep in mind that low West Coast SIM model is not a density dependent model. This is not a seaward model. This is just a regular mud flow model. So we cannot explicitly simulate saltwater intrusion, nor we can simulate any salinity effects of sea level rise. However, the direction of the velocity vectors can be an indication of movement of the saltwater interface that you basically, John was talking about the saltwater interface mapping, and then those maps, I will be using those maps as just as a reference, the well field locations. So what I'm showing here is saltwater interface and some public water supply utilities that are vulnerable to saltwater intrusion based on the proximity to the saltwater intrusion lines. Now, these lines, again, I know you've seen this line before, but those indicate the 250 milligram per liter chloride concentration. And then we have three different maps, 2009, 2014, and 2019. What I will be talking about is essentially I'll be looking at around Lee County area, Lee County utility area, and then Bonita Springs area, Naples, and Golden Gate area. And then looking at the Bonita Springs in lower Tamiami aquifer, and we see about 2 million gallons per day increase, projected increase. And here I'm showing the velocity vectors. On the left-hand side, I'm showing the 2014 reference condition figure, and 2040 is shown on the right-hand side. And in the middle, I'm showing this small figure just to give you a sense about the location of what we are looking at, and about the colors of the vectors. The blue color indicates the upward movement with respect to the top surface, and the red color indicates downward movement with respect to the top surface. And these purple dots indicate the location of the wells. And the purple line indicates the saltwater intrusion, or the interface between the saltwater and freshwater in Lower Tamiami Aquifer. Now, if you focus on this particular area close to the interface, you can see the velocity vectors are exiting from the well field and they are moving towards the saltwater interface, which is good. And then if you look at the 2040 condition, if you look closely, the conditions are the same. There's no big difference between the 2014 reference condition and 2040 future condition. The direction, especially I'm focusing on the direction remains the same. They are towards the saltwater interface. And then looking at the Golden Gate in Lower Tamiami Aquifer, again, this is the this figure shows the location of the Golden Gate well field and the location of the mapped saltwater interface position. So the increase is about 0.74 mgd. When we looked at the 2014 reference conditions near the saltwater interface, it's probably hard to see that, but the velocity vectors are pointing towards the saltwater interface. And when we go to the future condition, look at the same location, we don't see a big difference. We don't see vectors, direction of vector changing. Oops. Okay. All right, anyway, well, okay. So then City of Naples in Lower Tamiami Aquifer. And actually the projected increase from this well field is very small. It's like 0.03 mgd. Now this shows the location of the well field with respect to the saltwater interface. And if you look closer to the saltwater interface, you can see the velocity vectors are pointed towards the saltwater interface. And then in 2040 condition, again, you don't see a big difference. There's no change between the 2014 and 2040 condition. All right, looking at the Lee County utilities in Sandstone Aquifer wells. So here again, the figure shows the location and the location of the interface, which is shown in green color. And the projected increase is very small, 0.79 mgd. And actually only portion of this is coming from the clastic zone and the other portion is coming from the carbonate zone. So if you look at this saltwater interface, you don't see a big movement of velocity vectors, which indicates that there's no big flow going across the saltwater interface. So which means it's relatively stable. And I'm going to zoom into the area because it's kind of hard to see. See, there's no big movement. There's no velocity vectors indicating that any movement. If you go to 2040 future conditions are almost the same. They don't change, which is good. And then Lee County utilities in Sandstone Aquifer carbonate zone. Again, we see the increase 0.79, but only a portion of that comes from this aquifer, small portion. Now, looking at near the interface, if you focus near the interface, I'm going to zoom into this area because it's kind of hard to see. The direction of the velocity vectors actually away from the saltwater interface. If you can see these vectors, I know it's kind of hard to see, but this is the only case where we see the velocity vectors are going away from the interface towards the well field. And if you look at the future condition, there's a slight increase in velocity vectors you can see, now the velocity vectors are clearly showing that they're moving towards the well field away from the saltwater interface. But there's not a lot of big difference. It's just a small difference. All right, that brings me to modeling conclusions. Okay, so the lowest cost superficial and intermediate aquifer system model is a regional scale calibrated and peer-reviewed model developed for the superficial and intermediate aquifer system in the lowest cost planning area. And the model results indicate that 2040 demands can be met without any adverse impact to the existing groundwater resources or to the natural system. And we in fact saw some water level rebounded in Cape Coral area, especially, and also we saw some rebound occurring in southeastern Henry County because of the some of the decreases in projected pumping. And then wetland analysis, again, this means that we use pump soap scenarios. We have a couple of limitations with this type of analysis. First one is the model was calibrated with all the pumpings turned on, but when you turn off all the pumps, it becomes an extreme condition. We don't know how the model calibration will react to that. So essentially the calibration statistics won't be as good. So there's a certain uncertainty in the results when you're looking at the results. And the other important thing is we know the drainage and the other developments can significantly impact the wetland system, but we did not take that into account during this analysis. And so we saw some increases in wetland acreages associated with the increase of 1 foot or more drawdown with 2040 demands in especially in Collier County, Lehigh County, and some in Bates and Henry County as well. And we also saw some improvements because of the water level rebound occurring in southeastern Henry County in the future scenario. Continuing modeling conclusions and about the MDL or the maximum developable limit analysis. And we have a couple of limitations of this study. First one is the aquifer top elevations. Actually, those are obtained from interpolations. So because of that, there can be a plus or minus 5 foot error, which is a big limitation. And the other one is now all these areas where there's we saw where there are potential for MDL violation, model indicates that there are some agricultural withdrawals. Now, because the lack of metered data, we have used some estimated data using the model, another model called APSIS, and this may have some uncertainty also. And regarding the lower Tamiami aquifer, so the model indicated that near the Tri-County intersection area, there's a potential for future MDL violation. However, this area, we did not see a confinement above the lower Tamiami aquifer. And so essentially water table aquifer and the lower Tamiami aquifer essentially are the same aquifer. So there's a big hydraulic connection between those two in that particular area. And additionally, when we looked at the monitor wells, it indicated that actually during the 1 year 10 drought condition, which is 2007 May, we did not see any violation of the MDL in that particular area. And in Sandstone aquifer, again, we saw a very small area that can be potentially vulnerable for the MDL violation in the future in northern Collier County. And again, this area we did not see a confinement above the Sandstone aquifer. So the MDL analysis gets difficult when this type of situation occurs because we cannot clearly define the aquifer. Now, in addition, in this area, we saw that decline in future agricultural demands, and also there's no potential growth in this area. So, which makes the potential for any future violation in this area is pretty low. And in addition, we actually looked at the mid-Hawthorne aquifer MDLs. The model did not indicate any violation of MDL during any 1 in 10 drought condition. So the message is the close attention needs to be paid to this any potentially vulnerable areas in Lower Tamiami and Sandstone Aquifer in the future. Continuing modeling conclusions about the saltwater intrusion analysis. And again, this is not a density dependent model. This is a regular mud flow model. So we cannot explicitly simulate any saltwater intrusion, but the velocity vectors can indicate the direction, the movement of the saltwater interface. And looking at the direction of the velocity vectors, we did not see any major intrusion, lateral intrusion issue under current or the future pumping conditions. I guess that's all I have, and I'll be happy to take any questions.
All right, thank you, Jita. All right, if you have any questions, please raise your hand using the raise hand feature or *9 on your phone. Okay, I see several people want to comment. First up, Lee Worst.
Good morning, gentlemen.
Lee.
You had a slide, and it was the mid-Hawthorne aquifer, and it showed a 12-foot decrease in central South Fort Myers. Could you possibly bring that slide back up, please?
Sure. All right. Give me a moment. I've got a lot of animations going on here.
By the way, it was a very good discussion.
Oh, thank you. Oh, right here.
Okay, yes, sir. I noticed, and you quoted a 12-foot decrease in the mid-Hawthorne
Right.
from 20, and that was between an average of 2014 and 2040. The water level that you were seeing in 2014, do you recall what they were?
Yeah, actually, I had some graphics at the end of the presentation, if I can go to the.
Sure, sure.
Yeah.
I'm sorry, I'm working off an iPhone screen and it's really small. I can't see that.
Oh man, that's tough.
Yep. Oops. I went too far. All right, looking at the mid-Hawthorne. Okay, here you go. So
And-
the area we're seeing, it's it's somewhere between -10 and -40 in GVD.
Okay. That's you're in Collier County in that circled area right there. If you
Yeah.
could move up a little bit further north there.
This area,
If you could move the cursor a little further north and a little bit to the west there.
the west. You
And to
want to look at the Lee County or the Collier
Yes.
County?
Lee County.
Okay.
Central Lee County is what I'm looking
Okay.
for, please.
So it is somewhere between, I would say, -20 to -30,
Okay.
-40.
Just to give you a heads up, and that was the 2014. What was
That's-
and you say it was approximately 12 foot deeper in 2040, correct?
Yes, that's
Okay.
correct.
And I realize that this was a unique situation this year, but to kind of give you an idea, we saw water levels, and this is an AVD of -98 feet in AVD.
Ooh. Wow.
And matter of fact, Pete Kwiatkowski, if he's listening in, he can give you that data on the location of our wells. We now have meters on those. And that's mainly in the Daniels Road corridor, just east of 10 Mile.
Okay.
And we may want to focus a little more on that. That predominantly is not agricultural use. That is either commercial and or heavy domestic irrigation and or domestic self-supply use.
Okay.
And the
Yeah,
other the other question and comment that I'd like to let you or make you aware of, Pete can also show you our wells that we installed at in Gunnery and 8th and Lehigh Acres. We were seeing an approximate 30 to 31 foot difference from land surface to water level in the sandstone there. And I believe that was a negative, I believe we're at -5 this year is what we reached on that. And that was sandstone.
Oh, that was sandstone. Okay.
Yes, sir. Sorry. I wanted to at least brief you on both of those.
Okay.
And I realize that you're using 2014 and 2040 numbers. You haven't had a chance to update and calibrate your model, but that's too great of a water level difference not to try to look into, I believe.
Right. Yeah. I mean, the model calibration period ends in 2014. So yeah, we didn't look at the data from 2014 up to now. Yeah, that's very good
I fully
information.
Understand. I fully and thanks to Mark Elsner and Bob Barastro and Pete Kwiatkowski. They were all very, very helpful this year in our bad situation we had. In the water shortage we experienced this year, but this would be one of the stellar years to kind of mark out and kind of keep track of what happened.
Thanks, Lee. Good comment. And
All right.
thanks for your help and Lee County's help by getting us through that very dry period.
Gentlemen,
All right,
have a good day. Thank you.
Thank you.
Thank you.
Hi, Miss Roman.
I must have had that by accident, Mark.
There we
Sorry.
go. Nope, we can hear you now. Oh, okay. Mike Duver.
Can you hear me now?
Yes, we can.
Oh, good. I was just curious as to what time period that 1 foot drawdown in wetlands that they were talking about. Is that like dry season, maximum dry season? Is that a yearly average, or what's that criteria for the time period for it?
I'm sorry, I think I missed you on that a little bit. Are you talking about the wetland impacts that we looked at? Oh,
Exactly.
yeah, that's actually, we were looking at 1 in 10 drought condition. And we were actually specifically looking at 2007, but keep in mind that 2007 is drier year than 1 in 10. So it's 2007 May, because we use monthly stress periods. We're looking at results in each month. So we looked at the end of dry season, which is usually the worst case. So it's the 2007 May that you're looking at.
I asked the question because we've analyzed about 60 years of data at Corkscrew Swamp in our wetlands there. And we really didn't see any change, significant change in that hydrology until sort of the late 1990s, early 2000s or so. But since about 2000 or so, the hydrology in the swamp has gone from the sort of the deepest places we've got there, what they call the lettuce lakes, going from 1 in 5 years with the water table going below ground to 4 out of 5 years with the water table going below ground, and the water tables dropping down 2 or 3 feet below ground in that site. And there's actually a well nearby in the uplands that is showing a similar degree of drawdown in the lower Tamiami. So it seems like there's some other red areas out there that might be worth looking at. Yeah, it's right about where the LL is in Collier there along the border between Collier and Lee County is where the sanctuary is. Down a little further next, yeah, right in there.
Right here.
Right. Yeah. So we're very concerned about that. I don't know, maybe associated, as you say, that you don't include the effects of development or drainage, and that may be why you're not picking it up, but it's something that's definitely happening there.
Yep, and those changes, Mike, this is Mark, you know, those happening in the early 2000s, you know, our calibration period was right after that. And then we were looking at 2014 and 2040. So our simulation was looking at the, or part of it was looking at the, what I want to say, 2014 to 2040 post changes to corkscrew. You know, however, I know we have a study going on with it's Audubon to go ahead and look at that, and I think you've done some really good work in the past in the way of identifying what some of the numerous changes that have happened around that system in the watershed. You know, so with the ongoing studies, hopefully that's going to shed some more light on what's happened in that specific area.
Okay, thank you.
All right, Anura has his hand up.
Can you hear me?
Yeah, we got you.
All right, thank you. Good presentation. You had a couple of slides on calibration statistics. What are the basis of establishing those calibration criteria?
Essentially, we looked at our previous models, regional scale models, and based on that, we started the calibration criteria. And then when we started the peer review process, they actually gave us very good comments to improve the calibration criteria. For example, if you're looking at one of the things that they were concerned about, we are not, there's no better way to capture the transient response. The only parameter that the statistics that we had was the R squared, but that just represents how good the correlation is, but it did not really capture any, it didn't capture any errors. Like if you are off by 5 feet, then it won't tell you about that. So, so for that, one of the peer review panel members asked us to look at the transformed Nash-Sutcliffe coefficient, which is a measure of the essentially how good the transient response is. So this is what the transformed Nash-Sutcliffe, that value that we've used. I don't have all the equations handy, but we are in the process of completing the model report, and the report will be available in like 2 months. We will have all the details in that report. Basically, this will, this criteria was more stringent than just looking at the R squared value. So in addition to getting the correct correlation, you need to have the less error in terms of you're looking at the mean error. And the other ones, like residual means, we usually use this criteria for regional models, plus or minus a foot criteria. And these standard deviation, these are typically values from our regional models, absolute mean error, RMS error. And then also we wanted to have this, 50% or greater number of wells which are having errors less than 2.5, and also 80% of the wells that are having less than 5 feet error. So we just want to make sure that error is evenly distributed, which means there's no areas where we have a very good calibration and there's an area where we have a worse calibration. So this is a measure of how well the error is spread across the model domain.
So does that mean that as we get more data, it's possible that some of these criteria may be more refined in the future?
I don't think we will focus on any refinement of this criteria, but essentially the problems with these is like when you trying to get a better calibration, when you try to, let's say we are focusing on, instead of 1 foot, if you try to go for like a more stringent criteria, like half a foot, then what's going to happen is, because this is a regional model and we have like 1,000 feet by 1,000 feet, we can get that criteria, then we'll try to sort of overfit parameters, which may not be realistic. So we want to sort of stop at this sort of level so that we don't overfit parameters. And obviously, when you try to develop a local scale model, you can have a more stringent criteria than this. When you have a small size, much higher resolution than 1,000 feet by 1,000 feet.
Thank you.
All right, any other questions or comments? Please raise your hand. Okay, thank you.
Okay, hear me?
Yeah, who's that?
Yeah, is this Ken Fan? Can you hear me?
Yes.
Yes. It is a great presentation, and it's also very interesting. I do have some very small questions here regarding to that calibration input file. I noticed that you said you have updated those geological layers information into this model input. I just wondered, I think this model maybe will be used by the other sub-regional model. So what time and where then, if we want to use this kind of data, so where we can find it? And
so if you, if you want to get the hydrogeologic information, we actually have this report available. That was done in 2015. Okay. And if you want to get the other data, I think we will be able to, put them in a FTP site and send you the location if you want to get the model files, which includes all the data.
Okay, thank you. And my second question just here is, for those velocity vector analysis, I just have a question. You have like two arrows, arrows shows like upward and downward. Is that be physically meaning that you what's exactly mean like that one? Could you just explain? Is it upward and downward?
Yeah, when you, so the way this is calculated is if you look at a model cell, we have 3 components of flow or velocity, like horizontal 2 components and vertical 1 component. So to produce these horizontal vectors, you get the resultant of the 2 horizontal component. And then you also look at the vertical component, the 3rd component, and then you know which direction exactly, whether it's upward or downward movement within that model cell. Now that is calculated with respect to the top of the surface.
Okay, thank you. Okay. Yep. Yeah, that's anyway. By the way, it is a good job.
Oh, thank you. Thank you.
Okay. Any other questions or comments? All right, I would like to acknowledge our modeling team. As you can tell, this is a major effort in developing a model from scratch, going from the hydrostratigraphy, collecting all the pumpage data, well locations, through calibration and application, and through the dedicated effort of this team, made this available and able to present today. Going forward, our next steps, we're going to go ahead and discuss the comments and feedback that we received today, as well as any feedback that we receive after this meeting. Again, if you think of some things following the meeting, shoot us an email or give us a call. Be happy to hear those and discuss those. We're going to post the PowerPoint presentation on the Lower West Coast Plan webpage, and Bob will send out the link to that. Upon request, we'll make the model files available via download or on an FTP site. And as Udita indicated, we'll be finalizing the model documentation within the next couple months. And then this information will feed into the 2022 update to the Lower West Coast Water Supply Plan. So I'd like to go ahead and thank our presenters, John, Udita, very good job, very comprehensive. And just a nice delivery.
Thank you.
Okay.
Thank you, Mark.
Mm-hmm. All right, if there's no other questions, we have our West Coast Florida model at 1:30 this afternoon. So I think most of you are going to be joining us for that also. So have a good lunch. And if you haven't signed up for that, there's still time to register and participate. And thanks everybody for your participation in this meeting and the information as we were developing this model and speaking with you and giving us the data. It was definitely a team effort. All right, talk to you at 1:30. Thank you.